Welcome everyone to the lecture 6. So in this lecture we will be talking about carrier statistics, continuing from the last lecture. So again we will be following section 2.4 of the textbook by Pire. Alright, so in the last lecture we have seen the semiconductor material can be represented by a band diagram where you have EC, EV and then the Fermi level, and the number of electrons that you have, density of electrons that you have in the conduction band is given by n, which equal to nc multiplied with e power ef minus ec over kt, and k is the Boltzmann constant and T is the temperature. And here this quantity nc is called the effective density of states in the conduction band. And similarly the density of holes in the valence band is given by nv multiplied with e power ev minus ef divided by kt, where this nv is the effective density of states in the valence band. And for silicon the values are nc and nv are these numbers. Alright, so let's think about an intrinsic semiconductor, and first let's figure out where the Fermi level is for an intrinsic semiconductor. So as we have discussed that in an intrinsic semiconductor there will be equal number of electrons and holes, and that is what is called, so n equals ni, the number of electrons, and which is equal to the number of holes. Alright, so so essentially if n equals p, then what we can see is that nc e power ef minus ec over kt equals nv e power ev minus ef over kt, and this essentially gives you this relationship that ef minus ec minus ev plus ef equals log of nv over nc multiplied with kt, essentially ef equals ec plus ev over 2 plus kt over 2 log nv over nc. Alright, so now nv and nc, although they're a bit different, they're almost at the same order of magnitude. So essentially what happens is that this is a very small number, almost we can consider that it's almost equal to 0. So ef equals, you can consider it for at least for this class, ef equals to ec plus ev over 2, which means that this ef is halfway between ec and ev. So for example, this silicon, for silicon this ec minus ev is the band gap, which is around 1.1 ev. So this gap ec minus ef for an intrinsic semiconductor is around 0.55 ev, and ef minus ev is also 0.55 ev. Now this is valid only for an intrinsic semiconductor, that ec minus ef and ef minus ev are both equal to almost equal to 0.55 for an intrinsic semiconductor only. Alright, so now let's look at what happens if you have an extrinsic semiconductor, a semiconductor that is doped with either a donor or an acceptor. So, first, if the Fermi level is closer to the conduction band than it is to the valence band, then there will be a large number of electrons. Why is that? Because if EF minus EC is small, then N is large. So as EF minus EC goes down, your N is higher. So in that case, you will have more electrons in the conduction band. And of course, if that is the case when you have an N-type semiconductor, and if your dopant density, the donor density is Nd, then N will be equal to Nd. So now based on this relationship, you can actually calculate the value of EF minus EC for a given donor density. On the other hand, if the Fermi level is closer to the valence band, then you will have a large number of holes. So the closer the Fermi level is to the valence band, the larger the number of holes. Why is that? Because if as EV minus EF increases, the P also increases based on this relationship. And this is actually the case for a p-type semiconductor. In a p-type semiconductor, EF will be closer to EV, and for an n-type semiconductor, EF will be closer to EC. And of course, even an p-type semiconductor, the number of holes will be equal to the density of the acceptor dopants. And again, based on this relationship, for a p-type semiconductor, you can calculate the position of EF in the band diagram. Alright, so again, in an intrinsic semiconductor, the Fermi level is right at the middle of the band gap. In an n-type semiconductor, EF is closer to EC, and in a p-type semiconductor, EF is closer to the EV. Alright, so now again let's do some more quantitative analysis. So again, we start with these two equations. Now what you can see is that irrespective of whether the semiconductor is intrinsic or extrinsic, what you can see is that if you multiply N and P, what you would get is Nc multiplied with Nv e power Ev minus Ec over Kt. So this is valid for all cases. Alright. Now as we have already seen, for an intrinsic semiconductor, N equals P equals Ni. So if we take this relationship here, Np equals Nc Nv e power. So one thing to note here is that this Ev minus Ec, so Ec minus Ev is the band gap Eg. So what you are essentially getting from this relationship is this e power minus Eg over Kt. So here you have Eg over Kt, and for an intrinsic semiconductor this becomes Ni square. So Ni, the number of carriers in a semiconductor, in an intrinsic semiconductor, is square root of Nc Nv multiplied with Eg over KT over 2. All right. Now what we have said is that this relationship is true for any doping density. So what we can also write is that this is equal to Ni square. Where does it come from? It just comes from here, that this quantity over here is equal to Ni square. So we just write it here like this. So irrespective of the material, whether it's intrinsic or extrinsic, Np equals to Ni square. Alright, so now let's look at an extrinsic semiconductor. So for example, if you have an N-type material, what we have seen is that the electron density is equal to the donor density. So what we can write is that based on this relationship here, Nd multiplied with P equals Ni square, or P equals Ni square divided by Nd. So if you know the dopant density, donor density in an N-type semiconductor, then you can also calculate the number of holes in that semiconductor. Now as you can see that if Nd is high, your P, the density of holes, will be low. So the higher you dope a material with a dopant, the number of electron increases, and also that decreases the density of holes. Okay, so here this should have been p-type. So on the other hand, if you have a p-type material, your hole density should be equal to the acceptor density. So then you have n multiplied with Na equals Ni square. So your electron density in a p-type material is Ni square divided by Na. Right. So this is the electron density in a p-type material. So again, in a p-type material, the hole density is equal to the acceptor density. So the higher the density of acceptor, the higher the density of holes, and the higher the density of the acceptor dopants, the lower the density of electrons in a p-type material. Alright, so now let's look at a numerical calculation. So here you are given the density of acceptors in a semiconductor. So basically this material is doped with an acceptor. So this is a p-type material, and what you're asked to do is to calculate the Fermi level with respect to EC and EV. And then you are given these parameters, the value of KT, the intrinsic carrier density Ni, Nc, and Nv. Alright, so the way to do the calculation, I'm just showing a sample calculations, and you will be given a lot of problem based on this kind of calculation in the class. Alright, so the material is p-type, so because it's doped with acceptors, so the hole density will be equal to Na, and then based on the relationship we have seen here in the class, that Ev minus Ef is equal to KT ln Na over Nv, and then you would get this number here. So basically what it tells is that you have Ev here, Ef here, and Ev here, and Ev minus Ef is 0.119. So then this Ei means the Fermi level of an intrinsic semiconductor, and this Ef here means the Fermi level of this semiconductor. So then we know that the gap between EC and EI is 0.55 eV, and also this much is 0.55 eV. So the gap between EI and EF should be 0.55 minus 0.119. So this is wrong. So this should be 0.431. All right. And then this is 0.55. So this much should be 0.55 plus 0.431, which is 0.981. All right. And then the electron density here is simply Ni square by Na, and this comes out to be this number. Okay. So let's finish this lecture by comparing the mobility and typical carrier density in metals and in semiconductors. So the first thing that you will see is that in semiconductors, either N-type or P-type, this is a ballpark mobility, and the mobility in a semiconductor is usually much higher than that in the metals, almost 10 times or even more. But on the other hand, metals usually have a much larger number of carriers compared to the doped semiconductors. So in doped semiconductors, usually the doping is in the range of 10 power 21 to 5 multiplied with 10 power 24 per meter cube, while in metals it's of the order of 10 power 29 per meter cube. All right,